Hi all of you. Welcome to another lecture of nanoelectronics. Okay, the topic for discussion today is MODFET, MODFET and heterojunction bipolar transistors. Myself, Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MBC CET Pyramid, leading the session. MODFET. What is actually a MODFET? It is a field effect transistor having conducting channel at the junction of two dissimilar bandgap materials. A two-dimensional electron gas layer acts as the channel with very high mobility for electrons. The device is also called as HEMT, that is high electron mobility transistors. The electron transport occurs in a plane parallel to the hetero interface. The thickness of the layer is small enough so that quantum-sized effect occurs. The most important feature about the MODFET is that it is having an increased mobility of electrons in the heterojunction layer and hence therefore it is said to have more good performance. MODFET, the device structure, you have to learn this. A cross-sectional view of the MODFET is shown in the figure. The structure is very similar to that of the MOSFET except that it is having a conducting channel layer. Now it consists of a source, gate and drain as shown in the figure, and all these electrodes are present. The layers of MODFET are metal N-type gas, intrinsic gas and an insulating substrate. That is why it is written as I gas substrate. Okay, this is this basic structure. Now, one of the important characteristic of a MODFET is that it is having a two-dimensional electron gas that offers the flow of electrons with very high mobility. Okay, these are the basic structure and it has got a spacer that is here. I'll tell you what a spacer is. Okay, the width of the two-dimensional electron gas is nearly 8 nanometer. Okay, before that, the quantum well is formed at the interface due to larger gap of the gas, as compared to that of the gas. The electrons are transferred from gas to gas due to the difference in the electron affinity. Then it is sufficient for the quantum sized effect because the maximum thickness can be 14.9 nanometers. This we have seen already. In modulation doped heterostructures, two-dimensional electron gas is formed in the gallium arsenide structure. However, electrons may have some impurity scattering in N-type gas. This is provided by using an undoped gas layer which is called as the spacer. So the undoped gas layer as spacer signifies the effect of the MODFET. Okay. It isolates the conducting electron channel from the N-type gas layer that generates the carriers. Okay. It leads to higher electron mobilities due to reduced interaction with the ionized donors. The width of intrinsic gas and is about 5 nanometer. When the voltage is applied, source and drain conduction takes place in the two-dimensional electron gas with high mobility. Okay, we'll see all those things. The quantum well is formed at the interface due to larger gap. We saw that already. It is due to the larger gap of gas as compared to gas, the electrons are transferred. In modulation doped two-dimensional electron gas, gas is formed in gas. This is avoided by providing undoped gas layer which is called as the spacer. Then it isolates the electron channel from N-type gas layer that generates the carriers. Now it leads to higher electron mobilities due to the reduced interaction with the ionized donors. The channel current can be modulated by a voltage signal given to the gate. And we can see that the IV characteristics of MODFETs are very similar to that of MOSFETs. Now, coming to the advantages and applications, we have it can be operated in wide range of frequencies, low noise levels, and the cutoff frequency is much larger than corresponding values in silicon-based MOSFETs. The applications are signal amplification, and it is used in monolithic microwave ICs. Then they are used in cell phones and radar and radio astronomy applications. The next type or a next topic for discussion is the heterojunction bipolar transistor. It is actually a transistor with heterojunction instead of homojunction. The performance of transistor depends on efficiency of emission, transport and collection of charge carriers. In order to increase the performance, the emitter region must have greater doping than that of the base region. But this leads to the reduction in the band gap of semiconductor. Now these are the band diagrams of a homojunction bipolar transistor, and this is the band diagram of a heterojunction bipolar transistor. Okay, now that was the about the band diagrams in heterojunctions. Now we can see the doping level of an emitter can be lowered for reducing the parasitic capacitances of emitter base junction. It can be operated at very high frequencies. Then we have another concept called DHBT, that is the double heterojunction bipolar transistors. You also have to look through what it is. Then the advantages of this is the use of indium gallium arsenide, indium aluminum arsenide, or indium gallium arsenide or indium phosphide based heterostructures in HBT increases the operating frequency up to 200 gigahertz. Then you have then another advantage of heterojunction bipolar transistors is it is possible to integrate electronic and optoelectronic devices on the same chip. The most promising of all silicon compounds for the fabrication of the bipolar junction transistors are silicon germanium based alloys from which heterojunctions can be formed, since the band gap of silicon is only 1.12 electron volt while that of germanium is 0.66 electron volt. So it is easy to make this kind of things. Okay. Thank you for patient listening. Thank you so much.